Some of you will be right. Like somebody came to me and clearly I had just missed something. I do miss things. I make mistakes. So that's fine. But just make sure I make a mistake and make sure it's not just haggling over half a mark here and there, because I'm just going to remark the whole thing. And I tried to be really generous. And if you're just like hounding me for a few marks, then I might be less generous. Yes?
Is all of today's lecture going to be about the midterm or just the first bit?
I don't want to talk about the midterm at all, but I think people will want me to.
Okay.
So this is the distribution. I was actually really surprised, and I was glad in the sense that it has a peak and looks like a real distribution. It's not bimodal, it's not flat, it's not stupid. I didn't like a few things about it. I didn't like this. I didn't like that the average was 56%. I didn't like that 68% of the people got better than 12.5. So 68% of the people passed. There's actually a bit better statistics here. So 20 people got like better than 80, or sorry, 20%, or sorry, it's 11%. 20 plus people, or 11% got better than 80%. 27% got, I don't know what 16 is. 16 times 4.
64.
So, and then there was a big bunch in here. There's also a big bunch in here between 10 and 12.5. So I think that's roughly. I mean, it's really hard to, whenever you make a test, it's really hard to get that kind of resolution. So like, for example, when it comes time, for final grade, I would never give anybody 49 because I just don't believe I could ever get that kind of resolution. Whenever you do a measurement of some sort, there's always some uncertainty. So I would never trust my uncertainty so much to be less than 1 that I would fail somebody on that. Probably the same thing is true with 48. 47, and then I'm starting to get, no, that's probably okay. But that means, to me, I think all of these people are probably like right in there and could easily have passed this midterm. I'm a little bit more concerned about these people that are in the single digits. Sometimes there were some cases where it was just, no, in most of these cases there was just a lot of blank space. Okay, so if that's the case, I think you know who you are, and you also, if there's blank space, you know what you need to work on. You need to work on being able to fill the space with answery stuff. Right? There's a big difference between doing a problem and just like getting it wrong even, or getting it halfway done and not being able to finish it, and just writing nothing. And so certainly by the time the final comes around, you want to be able to write something. I'm going to go through quickly what these are, or like what the solutions look like. So the first two were just, the first two are just fairly simple first order equations. I meant them to be kind of gifty. I'm not sure what to say about them. Like I said, I'll take pictures of these and post them, so you'll have them.
I fucked up.
The second one, this one seemed to kill a lot of people. I'm amazed at the number of people that said, I can't remember what this integral is. I've said it before, I really don't give a crap what you can remember. You should be able to do it. You should be able to understand it. So you look at something like this, a squared minus x squared, you say, oh, if I make this sine theta, and then the only thing you have to remember is, that's the only trig identity I ever expect you to remember, is that one. And that's a pretty easy one. That and SOHCAHTOA, right? Those are the only things you have to know about trig. That's all of trig. Everything else is just like deriving it from that. So there was kind of, this question was kind of like a bifurcation. The people that got it right. And the people that didn't get it didn't get much at all. A lot of people wrote down, oh, I think this is 10, and I'll just write it like that. Of course, clearly, once you start going down that path, you're basically, in a bit of trouble. I will, be careful, I will try to never ask you to remember anything. I do expect you to be able to integrate, I do expect you to be able to do algebra, I expect you to be able to do the things that you have in the courses before you. So if you have credit for a course in differential calculus, I expect you can differentiate. If you have credit for a course in linear algebra, I expect you can find eigenvalues, things like that. And it's just, it's an expectation. The third one, you actually had to get an integrating factor, and then the answer is that. I think generally people did okay on that. If you knew to get an integrating factor, you did okay. What was the next one? Was that the one no, that wasn't the one I screwed. Oh, this is the one that caused me so much interesting grief. So basically, you find these R values, you get 1 plus or minus 3i, which is here, which means you have a sum of cosines and sines. And a lot of people did it like this. Sometimes people tried to use other forms of the solution, and then the algebra was a bit messier. In particular, one of the very common solutions that is people left it like this, and so I had to rederive what the answer was in terms of positive 3ix and negative 3ix. I didn't expect anybody to do it that way, but enough people did it that I had to go back and do it. And then I think just one person did it using amplitude and phase.
Yeah, I did it wrong.
What's that?
I did it wrong. I did arctan of 5 by 4 wrong.
Oh, okay.
Yeah. I mean, the arctan of 1/2.
And then this is the one that you could have interpreted it 2 different ways. If you actually did the question as it was written, which is I think the top, is that the top? Yeah, it was actually much easier then. It was so much easier to do it that way. Yeah, the way I had intended it was on the bottom here because I wanted to have 2 roots that were the same, and so you had to put that in. But a lot of people did it on the top and did it that way. Actually, they were equally easy questions, and I don't even remember whether, when somebody brought it up during the test, I was just so stressed out. It's like, oh, I made a mistake. Oh yeah. But then I was looking at it after, it's like, I don't know if I did make a mistake. I think maybe I wanted to do that, but whatever. Whichever question you did, you got marks for it. Oh, that's this one. Oh, wait, that might be in the wrong order then. Yeah, this is 5. So, this was question 5. Other people did it a different way. I integrated it once and then found a particular solution to this first order equation. Other people did it different ways and it was fine. I was actually surprised. There was a couple of people that did it. I'm like, oh yeah, that's fine too. I had just done it this way. Sorry, yeah?
What was, like, very specific question? Do you know the average for this question? Like, how many people got it right? Like, or even just got grades on it to begin with?
So the quick answer to that is no, I don't have individual statistics. But my impression was this question was actually done fairly well, but it was kind of binary. So I think there were a number of people, I could see that there were a lot of people that ran out of time, and so their answer to this question might have been rushed, or then their answer to the last question might have been rushed. And then the last question was basically right out of the notes. It was exactly right out of the notes. And so this is kind of a giveaway then. I often do this. I would like to do it, so I'll probably do it on the final 2. I'll put something in there that we've done in the notes. Okay, so if you're there in class, you're paying attention, you're writing down the notes, you'll go, oh yeah, this is right out of the notes. I know this stuff. And if you don't go to class, then you go, holy crap, he's asking us to do this, and it's hard. There were a lot of people as well that did this. So this isn't the only way to do it. you can also, so I assumed this, okay? And I assumed this because this is the way I did it in class, and I think it's easier this way. However, there was a lot of people that assumed, oh, it's a sine omega t plus b cos omega t. Then what you do is you plug it into the equation, you get a whole bunch of things, you know, times sine omega t, and then a bunch of things times cos omega t. Since the driving force is cos omega t, you have to say all of that equals, all the cos things equal f0, all the sine things equal 0, and then go through it that way. So I tried to follow all those and give people like full marks if they did it that way. That's absolutely fine. There was also, because this is out of the notes, and this tends to happen when I give things out of the notes, there was certainly some cases where some people would write down blah, 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 and then write down something which is actually like 5 or 6 steps away. And like, I have no idea how you got this. Like, this is not okay. Again, there's no marks for memorizing things. I want you to understand things because understanding is more robust than memorization. Oh, there you go. So that's that. Okay, and like I said, if you have a real concern, come and see me. I definitely make mistakes. Like I said, I marked whatever, 95 times 6 questions. So yeah, I'll make some mistakes, but just make sure they're my mistakes and not you saying, well, I don't agree that, you know, I did this wrong, but I don't think that should be worth half a mark. Because we're not going to have that discussion. I'm not going to do it. Because I've marked everything a similar way, so if you try and make an argument, oh well, you know, I should get half a mark more, then I would in principle have to go back and change everybody else who might have made that mistake and give them half a mark more. So and of course that's not something we're prepared to do, because I'd have to find everybody and blah blah blah. Yes? Right now? No, of course not right now, because we're right in the middle of doing this. But if you think there's something, I'll tell you what I'll do. I would rather do it this way. I'm going to post these solutions. I don't know how much I trust you guys, to be honest. If you think there's a problem, come and see, or just give me your test after. Write down what you think the problem is on it in pen on the first page, and then come and give it to me after. Okay? And we'll go from there. I'll look at it. Obviously, if I post the answers, and you know, there are certainly people that have, you know, during their test were erasing a bunch of stuff, and I don't want to get into that. I think there's way too much emphasis on this, like, oh, making sure everybody's not cheating and crap like that, and we've burned way too much energy on both sides trying to deal with that. So if you think I made a mistake, write out on the front page what the mistake is, give it to me, I'll look at them all the next day or so. Okay, and I did make some mistakes. I'm guaranteed to have made mistakes. Okay, now, there's one more thing about the midterm. So I'm not doing, so this is it again, the midterm. I'm not right now gonna do something with the midterm. I'm not gonna say, so that 56%, I hate that, right? To me, your average should be something like 70. Okay, that's what it should be. But I'm not going to mess around with this right now, because in the end, what I care about is what your final marks are. Okay, and so I'm going to worry about it at the end. Yes?
If you do, when you do function form, that might go, you just remove the total out of it as well.
Well, I don't know if that helps people, because there was on that question, I think that was the most well done question. And
yeah, so you add it as bonus and remove it from, so the other 22.
Yeah, we'll see. I'm not going to do any artificially things until the end, because I don't know how it turns out. And if I add marks now, I'm not going to subtract them later. You can't do that. Okay, so we're just going to see how it goes after the final. Okay.
Yeah.
Can you see it?
So now,
Once you
Now I want to do
Give
math.
me a sec.
He's so helpful.
Math is fun.
Yeah, I did.
Math is totally fun.
I think it's just a plus.
Okay. Who remembers what we did last time?
Lagrange, something.
We did something.
We did lost something.
Lagrange transformations.
Laplace, Lagrange
Laplace
is the sum by
transformations.
ZT
Yeah.
Lagrange Laplace thing.
Laplace.
Same thing.
The last thing we did was, so we defined the Laplace transform, kind of out of the blue, just, hey, this is a Laplace transform. Then, we calculated a bunch of Laplace transforms. For no reason, we generated this kind of thing, said, oh, this might be useful, and then calculated a bunch of them. And then at the end, I said, oh, well, this is useful for solving differential equations. So I gave a specific differential equation, which was the harmonic oscillator, which is, of course, my favorite differential equation. And then we derived the Laplace transform of that equation, solved it algebraically, and then found the inverse transform. And so we did, I guess, in principle, show that it has a use for solving these second order equations. Now, I think somebody asked, who was it? I think it was somebody here asked, why would we do this? This was way more work than just solving the second order equation. Way more work. So there's a few answers to that. Although I have to admit, today I was having a conversation with a colleague of mine, and I really struggled because I was telling them, and you don't get to use this against me. I said, you know what? I've never used a Laplace transform to calculate anything in my life. Like I've used lots of different techniques to solve lots of different differential equations. I've used like Fourier transforms. I've done things numerically. I've done all sorts of stuff. Never have I ever said, wow, a Laplace transform is the right way to solve this problem. So I don't have a good answer for your question if your question is, when are these going to be useful to me? Because they've never been useful to me. I'm not in charge of the syllabus, so I can't answer that. One of the things, though, that is useful, or not useful,
Kind of useful.
I'll call it useful, it's not the right word, about Laplace transforms, is whenever we're solving any sort of differential equations, especially this showed up with first order equations, we have a bunch of different types of techniques, right? And you're like, well, what should I do? Should I find an integrating factor? Should I use a homogeneous particular solution? Like, how should I do this? And you kind of had to get a feel for it. Now, the nice thing about Laplace transforms is that in the end, there's no guessing the right technique. It's always the same thing. You write down the transform of the differential equation, you do some algebra, or like we'll show maybe today, maybe Wednesday, sometimes some calculus, and then you find the inverse of it. It's a method, it's like a recipe. So you can always solve equations using it. Sometimes it allows you to solve equations we don't have any other method for, and sometimes it's equally difficult. So one of the things we'll get to, again, maybe today, is we can also use this to solve second order equations that don't have constant coefficients, things that right now we don't have a technique for. But as it turns out, the examples I'll give you where we can use Laplace transforms to solve the second order equation, these are kind of few and far between. These will be very special examples that are made just so I can demonstrate for you, but in general, if I write down a second order equation with non-constant coefficients and try and solve it by Laplace transforms, it's going to be too messy. So I'm going to show you that we can do it, but it's not a good general technique. It's generally too messy. Yeah?
Isn't it used in electrical engineering for time domain transformation?
Sure. I don't know, I'm not an electrical engineer, I don't care what they do. It's good for discontinuous functions, it's good for things like that, but like I said, I've never had it, but I'm an experimentalist in self-condensed matter. What the hell do I know about Laplace transforms that are very useful? But the guy I was talking to, he's a theorist, also in self-condensed matter, but he's a theorist. He solves, you know, partial differential equations all the time. He's also never had a reason to use it. So maybe if you're an electrical engineer in some field, you'll use it. And we have to teach it because it's in the curriculum, but yeah, I find it hard to get too excited about it. So I understand your pain. Now, one of the things I will give you during, so I'm going to post this. This is a table of Laplace transforms. Now, actually, I was going to do something else. Maybe I'll do this first. So remember, so let's remember this. Let's see this. So we said the Laplace transform of y of t is the integral 0 to infinity y of t e to the minus st dt. And what we've done so far is we've used this definition, we've calculated a bunch of transforms and blah blah blah. Yes?
Can you zoom in a bit?
Is that zoomed in enough? So ideally, and we're going to find this when we do Fourier transforms, with Fourier transforms, the inversion formula is really nice as well. Actually, the inversion formula looks a lot similar to this. And actually, yeah, in principle, in some ways, it's a little bit easier to do Fourier transforms first, and then you can do Laplace transforms as kind of like a particular, as it's similar to Fourier transforms, but for some reason, that's not the order it's typically done in. Now, the inverse Laplace transform okay, and this is why it's messy. Let's suppose I have, I'll call this y of z. And then this path that we end up doing, so z is, oh sorry, yeah, x plus iy, this is x, this is y, this is this path here, gamma minus I r. Don't worry if you're not like really comfortable with this, because that's the whole point. Yeah. Well, sorry, I guess I should write it as, yeah, it is that. So the way you actually invert a Laplace transform is this. This is called, this thing here is called, this is a special contour integral. You do this in the complex plane. You integrate like this. Often you evaluate it by something called residue theorem. In other words, there'll be poles in the inside of here, and you do all this complex analysis. It's a complete mess. It's difficult. Inverting a Laplace transform through this way is difficult. Now, if you go on the internet, okay, the internet has lots of great things, and if you Google invert Laplace transform, you will almost never see this. As a matter of fact, you have to really struggle to see these. You have to write like Bromwich contour, blah, 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 or, other such things. Generally what you're going to find, okay, and there's not even any point in writing this down, but whatever, you've all written it down. Generally what you're going to find is this. Generally what you're going to find is that, well, I know that if I have, say, a over s squared plus a squared, the invert of that is sine. And so generally the way people are inverting Laplace transforms is by generating tables of transforms and recognizing these things on the right side to go back to the left side. Okay? So there is an analytic way of generating or of calculating an inverse Laplace transform, and we will absolutely never use it. And as a matter of fact, most people in their lives, even people that do calculate a lot of Laplace transforms, will never use it. Oh, but that reminds me, I have inverted a Laplace transform once in my life. If you solve viscoelastic problems anyways, you're using that method? Yes, using this method. It's not very hard actually, but it means you have to learn complex analysis. So let's do. Wait a minute. Okay, so before we get to that, let's just do some more practice. Calculating Laplace transforms. And then we'll do some inversions the way I said, not with that messy integral thing. Oh, you can't read that? So let's say that y of t is e to the 3t plus cos 6t minus e to the 3t cos 6t. And the way we're going to do this, where did it go? Yeah, there it is. The way we're going to do this is we're going to use this thing here, right? We're going to look at our Laplace transform sheet, and you will always have this. And the first thing I look at is say, oh, e to the 3t, so that looks like this one here, rule number 2. Okay, and so this one here, rule number 2, what's that going to be equal to then? What's the Laplace transform of e to the 3t?
1 over t minus a.
1 over s minus 3. What about this, cos 6t? What's that going to be? Yeah, or 36, whatever. And there's going to be, now I've got an e to the something and a cos together. That looks like a big mess. But thankfully, there's one like that right on our table. So e to the at times cos bt. This is going to be s minus a. It's going to be minus because the minus is still there. So this is s minus a. And then it's got s minus, sorry, it's not a, it's 3. Don't let me do stupid shit like that. S minus 3 over s minus 3 squared plus 6 squared. Now, this one here, just for fun, this one we used, e to the at cos bt. That's actually, I think that's not too bad to do, right? Like, let's try that. Let's try and find Laplace transform of e to the at cos bt, just to kind of be able to do some of these transforms. Well, one of the ways, well, first I'll ask, does anybody have an idea of a good way to solve this? How should we do this? Yeah?
Integration by parts?
I don't want to do integration by parts. It's too hard. Does anyone else have another idea?
Sorry,
Construction worker.
No, it's the Spanish Inquisition. Nobody expects the Spanish Inquisition.
Okay, forget it.
For the coast, the Laplace is just s over s squared.
For the coast it is, yeah. But,
No, you have an S squared.
Yeah.
it's an S, not an S squared. Yeah, okay, thank you. Yeah?
To answer your question, so we rewrite most of 60 as like e to the, rewrite it as function of our system.
Of what?
It'd be like e to the I6t, but then you only get the root part.
Oh, so you mean like if I write e to the at cos bt, this is the real part of e to the a plus ib?
That's exactly it.
Yeah, okay. Right, so let's do that. Let's realize that's the case. And so let's do this one. Let's do the Laplace transform of e to the a plus ib. And then in the end, let's remember that I just want the real part. That's all I care about. So if I do that, this is 1 over s minus a plus ib, right? And so now I need to make this in real and imaginary parts. So this is s minus a, minus ib, okay? And now in order, I don't like having imaginary things on the denominator, so I multiply by s minus a plus ib over s minus a plus ib, because the only things I'm allowed to do are multiply by 1 and add 0. Yeah?
Did you lose a t in the e to the a plus ib?
Times t, yeah. So if I do that, I get the Laplace transform of e to the a plus ib times t equals 1 over s minus a squared plus b squared. And then on the top, I get my s minus a plus ib. So then the real part of all this is s minus a over s minus a squared plus b squared. And now I've also got a way to do the sine one, right? Because I can get the imaginary part. So this was just a nice little aside that helps us calculate one more of these things. Now, I would expect, so I'm going to give you, like I said, I'll give you this giant table of Laplace transforms. You know, I would expect you could calculate a lot of these on your own. I could ask you to do some of them and it would be fine. And then there are some of them that I would never ask you to do. Okay? For example, let me ask a question here. How would you do this, the one with hyperbolic cosine as opposed to hyperbolic sine? Does anyone have an idea how they might do that?
I don't know.
Yeah.
Yeah, you can just put it into the exponentials, and then what is the definition? So what is the definition of hyperbolic cosine?
No idea.
Say, of x. What is hyperbolic cosine of x?
No idea. No idea.
Is it like...
We didn't learn hyperbolic cosine.
Nobody told us what that meant.
Yeah, we did.
We did. Somebody only told half the class.
Then you tell us what it is.
Holy crap, that was so rude.
When did we learn this?
Oh, it's just like, what?
Did we?
It has nothing to do with cosine except for this, right? Like, so cos x is e to the ix plus e to the minus ix over 2.
What?
And right? So it's just an, oh, sorry. What the heck am I doing? Moron? Okay, it's just exponentials, but it's also like the cosine of an imaginary, like the minus of an imaginary x. So you can get there, if you take the cosine of imaginary angles, you get things like this. And you might think that's a stupid thing to happen, but it actually happens all the time. For instance, if I do Snell's law at an interface, okay, I get like, you know, n1 sine theta 1 is n2 sine theta 2. So sometimes your refractive indices can be imaginary. They have imaginary components. That means there's attenuation. And so this imaginary trigonometry shows up all the time. And as a matter of fact, in that case, it's really important because when I have that, it means that you get into something called evanescent waves that way. So you can actually have waves that propagate very near the surface because they have this e to the minus x in them, rather than a propagation which would be e to the ix. So e to the ix means in this medium it propagates and it goes on forever. That's transparency. Okay, and if it's e to the minus x because it has a complex refractive index, then you have this attenuated wave. So that's actually something useful. Okay, so now we have this. Oh, that's actually the end of it then. Okay, somebody had a question over there. There was a hand up, or maybe somebody was just tired. Okay. Here's another one. Well, actually, I'm not even going to tell you this one. I'm going to Laplace transform. I'm going to. And it turns out that, oh sorry, minus 1 to the n. This is a really neat one, okay? And this is, we'll use this one in a little while. If I have t to the n times some function, so where I know what the Fourier transform of that function is, it ends up being in the derivatives of that transform. Now this shouldn't be that much of a surprise because remember when we took the derivative of, when we took the Laplace transform of a derivative, it was the same as multiplying it by s. So the first derivative of the transform, Laplace transform of a first derivative was s times the transform. So it's not that surprising that if I have t to the n times a function and I take this Laplace transform, that I get derivatives on this side. But I will not ask you to derive this, but it's a common one. And where does it show up? It shows up here, it's number 30. It's not always number 30, by the way. So if you Google, again, Laplace, table of Laplace transforms, you will get tons and tons and tons of ones. And actually, if you find a better one that you like better than this, let me know. I just thought this contained all the ones that would be useful without having too many other ones. So like an example of this that we'll use later is the Laplace transform of, say, t g prime of t. Wait, why do I have g prime of t? Yeah, I do have that one. Laplace transform of t g prime of t, or this is y. So I won't call it g. So this is going to be, let's just use this formula. So this is a first derivative, so this is minus 1 to the 1. And then I'm going to have a derivative of the Laplace transform, so it's dds of the Laplace transform of y prime of t. And then we remember this, okay? The transform of the derivative. We did this last class, but it looks like this here, number 36. This is that's the second derivative. Wait, where's the first derivative? Oh, right here. Here's the first derivative. Okay, we did that. We derived it in last class. How did we derive it? Who remembers how we derived that one? What technique did we use? Math? Yes. By parts, more specifically.
I have a question about that. In my notes, like, I don't know, I'm pretty sure I wrote everything down correctly like last time. I have the y at 0 is plus, but on the table.
They're all negative. Yeah, they're all
They
negative.
should all be.
Yeah. So that means this is minus 1, again to the 1, dds of, now the Laplace transform of y prime, we said this is s, y of s, minus y of 0. Okay. So now this is minus, and now I have to differentiate this. It's a product rule. So this is minus y of s minus s y prime of s, and then this y of 0 doesn't matter. So that means now, right, the Laplace transform of t y prime of t equals minus y of s minus s y prime of s. So it's a little bit annoying in the sense that one of the things I said before was a benefit of Laplace transforms is it takes these differential equations and makes them into algebraic equations. One of the kind of complications or whatever of that is that also I can sometimes take algebraic equations and turn them into differential equations. Sorry, you have a question?
Yeah. Why did you say that the y0 is not 4?
Because I have to differentiate it. So it's dds of a constant, so it doesn't matter. Right, I've got dds times this, which is just a constant, so I just throw it away.
No, with this branch position. That's what they said.
Okay, so now we know how to calculate transforms. We know that if I'm going to solve differential equations, I'm going to take the differential equation, I'm going to transform it, and I'm going to get this thing in terms of s's. And if I want to get back my original function in the time domain, I have to invert Laplace transforms. We also know that inverting Laplace transforms using this contour integration technique is stupid, and we're not going to do it. It's not stupid, it's colossally elegant, it's beautiful mathematics, and we're not going to do it. Okay? What we're going to do instead is we're going to say I've got my table, and I'm going to make things look like the table. And once I make it look like the table, I look here, and then I just go there and I write it down. Okay? That is the only way you're going to do Laplace transforms, I suspect, for your entire university career, not just now. Do you have to take a course in complex analysis ever?
What?
No. Okay, so then this is the only way you're ever going to do it. Well, you can't do one in the past now. That makes no sense. Okay.
There's one 2 years ago. Are we on the second year?
So let's do some examples. Okay, so let's suppose we've done some stuff, we had an equation, we end up with what do I have here?
Is that 35 minus 5?
Why did I do that? S to the 5. I mean, two things that look like each other.
Oh no.
Yes.
Sorry, is that 35 minus s? Or 35 minus 5?
That's 3s minus 5.
Okay, thank you.
So I will say the words. This is 19 divided by s plus 2 minus 1 divided by 3s minus 5 plus 7 over s to the 5. Okay, so let's go to let's do the first
This is
term.
what happens when you put letters in.
Okay,
We should just not have letters.
so I'm gonna do, well, let's read it like this: 19 over
Reject modernity.
1 over s plus 2, because then I can just do that one. No. Minus 1 over, and let's make this look a little bit different too. Let's make this look like minus 1/3, and then do 1 over s minus 5/3. Okay. And let's do this. I'm going to make this look a little bit different too, and maybe it seems like I'm being stupid, but I'm going to do this 7, and then I'm going to multiply it by 4 factorial, because why not?
Sorry. Sir.
I'm not sir.
Sir, Professor. Please add a dot between the 7 and the 4. Thank you.
So you don't know what 74 factorial is?
Not off the top of my head, no. Your calculator stops after what, like 30 factorial?
69 factorial.
Oh, thanks.
Still not 70.
Okay, so why would I do this?
And profit. We are not a cult. We are not a cult.
Like twice. You need
Why would I do this? Well, I do this because this one here,
What did you
is
do?
the inverse Laplace transform of 1 over s plus 2?
Just
So
looking
maybe
at
let's go
the normal eye function.
here. Oh yeah, it's like this, but except a in this case is -2, right? So that means this is going to be e to the -2t. So let's write down this is
Yeah, sure.
so inverse. So this is going to be 19 times e to the -2t minus 1/3. And now what is this one going to be?
the same thing.
Yeah, e to the 5/3 t. That's why I wrote it like that. And what about this one here? Why would I have done this? I multiply and divide by 4 factorial. I'll write s to the 5 in terms of s to the 4 plus 1. Why would I do that?
Fun and profit.
It's confusing.
Well,
the t to the n one?
Because,
yeah, it's the t to the n one, but where's... Yeah, okay, so sorry. I was looking at this one because this is the same thing as this, but this is not for integers, so...
T to the 4, and then with the 7 over 4 factorial on that.
Yeah, exactly. So this is just t to the 4, and then I've got 7 over 4 factorial, so that's 7. 4 factorial is 24. And then this is t to the 4. So again, we took this, we kind of manipulated it so it would look like elements on the table, and then we just recognized those elements and did it. This? Yes. Okay. So t to the p, this is p greater than -1. So you notice number 3 is for integers, right?
You?
This is not for integers. Right. But the gamma function, right,
Yeah, function.
what?
what is this? Is gamma of n plus 1? Is that n plus 1 gamma of n? And then, what's that?
What is
Well, the factorial is a specific case of a gamma function.
Yeah, like I know that
Are we
n
gonna
factorial
use
is gamma of n plus 1. I think. Like it's just shifted by 1.
Yeah, and I'm just trying to remember which way it is. So this would be
I'm pretty sure it's like
the other way around. Oh, you mean gamma of 1 plus 1? Sorry. You're saying this is n factorial
if n is a
if n is an integer.
integer.
But in general, that means. Okay, I'd have to look it up to see.
F of like it's the gamma of x plus 1 is equal to x times gamma of x.
Is that what it is?
Yeah.
Oh, sorry.
X of gamma of x.
Yeah. But this is true for anything. This isn't just true for things, and so you can do this for like a half. You can do it for 3/4. You can do it for any number. You can do it for pi. I don't know if you can do it for a integer. No, it has to be greater than -1. Yeah?
Why is insertion -1? Because it cannot
I don't know. Not right now, I don't know. I don't know offhand. I think because 0 factorial is 1, right? But then I can't do anything less than that. So gamma of -1 plus 1 is fine, right? But I can't have, yeah, I don't remember, and I'm not prepared to talk about it without screwing up.
I think they're all the initial condition for that though, right? So like you define like kind of like how you get from one step to the next.
Oh, yeah, sure. There is gamma of things that are like less than 1, like gamma of a half is root pi.
Yeah, so you just like say.
So you get it down until you get to that one, and then you have to do an integral. You have no choice. Yeah. Anyways, that's your answer to the question, though, is that this p here doesn't have to be an integer. It can be anything. But then in the end, you're going to end up with something, gamma of something in the end between 0 and 1, and you'll have to do an integral to calculate it. Okay, let's do, oh, I want to do another example.
Yay, example.
I want to do lots of examples.
Is this also an inverse Laplace?
Sorry?
Is this
This is
also?
also an inverse Laplace transform.
Okay.
So let's say I have f of s. Yeah, this is a fairly easy one. 6s minus 5 over s squared plus 7. One of the things you'll notice, though, is that there's a lot of things, like with the exponentials, there's an s minus a on the bottom or an s plus a on the bottom. And so what it means is a lot of times when you're calculating inverse Laplace transforms, it's all about partial fraction decomposition. So if you love partial fraction decomposition, who doesn't, then this is going to be your best friend. If you hate partial fraction decomposition, then that sucks. So how would we write this? Let's write this as 6s over s squared plus 7 minus, and again I'm going to write it in a different way again, a little bit of a weird way. I'm going to write this as 5 times root 7 over root 7. And I'll do it like this here just so we can see why. Well, this first one here, what is this going to look like? It's going to be 6, and then it's s squared over s squared plus 7. So what is that?
Cosine?
Cosine of what?
Alpha of d. I don't know what I'm guessing.
Root 7 times t.
Hey, my close.
Because it's, remember, it's
Eight.
s squared plus a. Where's the cosine? It's s over s squared plus a squared.
Right.
So a squared in this case is 7.
Which means
So a is root 7. And the same or similar here, I'm going to have a 5. Now, when I do sine, it's s squared plus a squared on the bottom, and there's an a on the top. A is root 7. That's why I multiplied this by root 7 over 7. So this is going to be 5 over root 7 times sine root 7t.
How do we recognize half the shot? How do we see that?
Well, when you know, again, because we're not going to calculate things in Laplace transform, you want to get things that look like this. Because these are the only things you know. This is your knowledge. And so you have to take whatever you have and make it look something like this. You know, for instance, if I get this, oh great, I can just write it down. Okay, but you have to make it look like one of these things.
So it doesn't matter.
So the best way to do is to just do a bunch of different examples. Let's do another example. Every example has a different level of complication, so we'll do another one. Okay, let's say that f of s is 1 minus 3s over s squared plus 8s plus 21. Now this doesn't look like any of those things, right? It doesn't look like s squared plus a squared, so that's stop. So what are we going to do? Okay, if I look here, I'm just gonna put this on for a sec. I've got a lot of things on the denominator, s squared plus a squared, s squared plus a squared, s squared plus a squared. Yeah, I want it to look like that. This doesn't look like that. So what can I do to this to make it look something more like that? Very, very popular technique, yeah?
The quadratic equation?
Or, well, okay, yes. When you derive the quadratic equation, you do it by what?
Pythagoras theorem?
Sorry?
Completing the square.
Completing the square.
Oh, that's a thing.
Yeah. So what we do is we write. This is the reason you don't have to remember the quadratic equation even.
But the
Okay?
quadratic equation is so
You just
easy.
complete the square every time. What?
Quadratic
So s
equation
squared
is
plus
easy.
8s plus 21. Well, I know if I want to have an 8s, I can write this as s plus 4 all squared. That's going to give me s squared plus 8s, but then it's also going to give me 16. Well, I've got 21 on here, so all I need is 16 is 5 more. So this and this are the same thing.
Planning square makes so much more sense now than it did in grade 10.
Why didn't they teach us that way in school?
Because we're stupid.
And so let's have a quick kind of, I want to have a quick show of hands who uses or who can use the completing the square and derive the quadratic equation. Who's comfortable doing that?
We
It's
went
kind of what
through
they
in high
made you do in grade 10, isn't it?
Sorry?
You guys never, so hold on a second. You've never, or who has not completed the square with this? And then complete the square? Right, like you do this. You mean x squared plus b over a, x plus c over a, you mean like that. And then you say this is x plus b over 2a all squared plus c over a. Now I've added b squared over, so I have to subtract it like that. And then you just do a bunch of algebra and you solve for x. And that's how you get the quadratic equation.
That's so much easier than what they showed us in high school.
No, that's exactly.
I'm assuming that everybody's done this at some point in high school and they've just forgotten.
Yes.
It's been so long. Okay, so now we've got this. So I can write this then as,
Do you know basic algebra?
now I write f of s.
I don't know her either. She's elusive here.
Right.
Minus
I want to write this as 1 minus 3, and I'm going to write this, s plus 4 minus 4.
Of course you are.
The reason I want to do this, and again, this is s plus 4 squared plus 5. And the reason I want to do this is now I can write the top as minus 3 onto s plus 4 plus 13 over s plus 4 squared plus 5.
Oh, okay, that makes sense.
So this is algebra. It's again the same sort of thing. I'm doing, I'm completing the square. I'm adding and subtracting 4. I'm doing all this stuff just because I want it to have in a form like this. Because I know with this, I can write down what the solution is. So this is minus 3 s plus 4 over s plus 4 squared plus 5 plus 13, and now I'm going to write this as and the reason I'm doing this again, why am I doing this?
to mess with this.
Where's my sheet of,
We're doing this to mess.
great, here we go. The reason I'm doing this is because now this isn't quite the same as cosine, okay, but it's that shifted version, and that is right here. Number 19 and number 20 are what it's going to look like now.
Okay, why do we need to root 15 over 15?
So that means I can write this as minus 3, and this is going to be, sorry, this is going to be, this is s plus 4 over s plus 4 squared plus 5 squared, so that's going to be, where is that again?
No idea.
This is e to the minus 4t cos root 5t, okay, because that's this one here, okay, and I've got a is minus 4, okay, if a is minus 4, and b is root 5, and it looks exactly like that. So it's minus 3 times this, plus 13 over root 5, and then this is going to be the same sort of thing. This is going to be e to the minus 4t, but in this case it's sine root 5t. Now, there was a whole bunch, sorry, and I'll write this as whatever, f of t equals that. There's a whole bunch of times when we were doing second order equations where we'd have, you know, e to the minus something times t, and then we'd have sines and cosines. So all of those equations are going to have solutions which look just like this. Okay, so I could have taken any one of those, I could Laplace transform them, I could go through this, I would go through this algebra rather than the process we did before, and I would come up with those answers. Yes?
Hi,
Hi.
so
Sine.
I'm just trying to, I'm having trouble wrapping it in my head around the purpose behind the root 5 over root 5 and the root 7 over root 7 previously.
Okay,
So
it's
can you
because,
explain that, please?
yeah, so for instance, remember that Laplace transform of sine at is a over s squared plus a squared.
Right.
So that means if I have something, I need this a and that a to be there. So for instance, if I have, well, let's go to this one. Let's go to this one. Laplace transform, or sorry, let's suppose I have, I'll do the one that I had, 13, and I'm just going to say s squared plus 5, right? I'm going to get rid of the exponential part there. Well, I want it to look like this. Well, 13 squared is not 5. So what I need this to do is I need this to be root 5. The bottom is root 5 all squared, so I need the top to have a root 5 in it. And so what I do is I write this as 13 root 5 over root 5,
Because
and then this is x squared plus 5. And now all I want is I just want the one root 5 on the top to make it look right. So that means this is going to be 13 over root 5, and now it's root 5 over s squared plus root 5 squared.
Oh.
Because I need it to look like this in order to use the table. And it was a horrible choice to have 5 and s again. I seem to do that all the time.
Thank you. I get it now.
Okay. All of that took way longer than I wanted it to. So there's a few other types of examples I want to do, and they're really cool examples, but I'm not going to start them now because I want to give you a chance to give me your midterms and bitch at me.
Really to the start.
Yeah, I will post this table on the Learn page, but you don't have to use just this table. You can use any other table you want. The odds of you finding out a table with your exact thing are unlikely, but you could, yeah, I'll post this. I meant to do that today, but I didn't. So I'm going to stop there, and I'm going to let you come forward if you have any problems with your midterm. And I will see you on Wednesday to do more inverting Laplace transforms. Yeah! Laplace!